Okay, today we're going to look at number sets and set and interval notation. For number sets, the capital N in mathematics as the number set stands for the natural numbers. So these are the counting numbers, 1, 2, 3, 4, etc. Okay, they're always positive. Sometimes it includes 0. It depends on the context, but yeah, so all of the non-negative counting numbers. Z stands for the integers. These are positive or negative. So this is negative 4, 3, negative 2, negative 1. So positive or negative natural numbers and the number 0. Okay, Q stands for rational numbers. So rational numbers are any number that can be written as a fraction. So this includes common fractions. It also includes all of the integers and all of the natural numbers. Like the number 2 is an integer and a natural number. But we can write 2 as a fraction simply by putting it over 1, right? Any decimal, so like 0.58, that ends or is repeating, we can write as a fraction as well. So like 0.58, that's equal to 58 over 100, right? That's a fraction. And any repeating decimal we can write as a fraction. So like 1.2 repeating, we can write as a fraction. If you're interested in that, there's an extension at the end of this video that you can watch. So rational numbers can be written as a fraction, or they're repeating decimals, which can be written as a fraction. Okay, I stands for irrational numbers. Okay, irrational numbers cannot be written as a fraction. So if it's a decimal that never ends and never repeats. So a classic example of this is the number pi, which we estimate to be about 3.14, but we know that pi repeats on and on forever and ever, in fact. Okay, so here you can see the first 100,000 digits of pi. So you can see it's 3.141592, etc. Yeah, and I was wrong when I said repeats. Pi doesn't repeat. The digits don't repeat. So it's a decimal, it never ends, and the digits never repeat. They just go on and on and on forever after the decimal place. So pi is an irrational number. Another example is surds. So like the square root of 3. You'll notice if you do that in your calculator, it actually, if you find the decimal of it, it doesn't repeat and it continues on and on forever. Any surd will do that. The square root of 2, the square root of 5, etc. Okay, but the square root of 4, for example, is a rational number because it can be written as 2, which can be written as a fraction. Okay, so only surds, only the radicals that are already reduced. Okay, and then R stands for all real numbers. Okay, so everything that we're going to look at this year is a real number. As you continue on in your studies of mathematics, you'll look at complex numbers, and those have a real and an imaginary part. But everything we'll look at this year is real numbers. Complex numbers refer to an imaginary part that is taking the square root of a negative number. So for example, -1, the square root of that is the number I, but we won't look at that this year, just to be curious. Okay, so we're gonna do a little diagram of all of these numbers that we've just looked at. So if we think about this big rectangle here, so the outermost rectangle, encompassing all of the numbers that we're going to look at this year, that's going to be R, standing for all the real numbers. Okay, the majority of those will be rational numbers. Okay, so again, that's anything that can be written as a fraction. So a decimal that ends, decimals that repeat, yeah. And then we have irrational numbers. So they are non-repeating decimals that do not end. Okay. Then we have, what do we have? Integers. So those are Z. So integers are positive or negative whole numbers. Okay, and then we've got the natural numbers. So those are all the counting numbers. So any positive whole number, sometimes 0. So like 300, the number 2, the number 58, etc. Okay, so how we read this diagram, 58 is a natural number, but it's also an integer. Okay, so as we move outside of the diagram, so 58 is a natural number, it's also an integer, it's also a rational number because we can write it as 58 over 1, right? And of course it's a real number. The square root of 3 is an irrational number, and then as we move outside of the diagram, it's also a real number. 0.3 repeating is a rational number because we can write it as 1/3. And it is also a real number. Okay, so hopefully you can see the smaller the box, the more it applies. So natural numbers are integers. Integers are rational numbers. Rational numbers are real numbers. Okay, we're going to look at set notation and interval notation. It's really important that you understand set notation. Interval notation is an added bonus. So set notation, first of all, the little inequality sign here, the alligator mouth, so that part is going to eat whatever is larger, okay? So hopefully you remember that. So for example, if we have the numbers 1 and 2, well 2 is larger than 1, so we make the alligator mouth facing the larger one, okay? Okay, and we should be able to communicate with these. By the way, the alligator mouth can go the other way, so if we have 2 and 1, 2 is larger than 1, so it's going to face this way in that inequality. Okay, when we're reading these symbols, it's not so important that you use these brackets and use this part of it, but I'll let you know what that means just in case you're curious. But what is important is that you have this part of it. So this reads the set of, that's what the little squiggly lines mean, they represent a set. The set of all values x. So that's what this is here. It's defining what our variable is. We don't really need that for the purposes of our class. Can be such that is what this line is right here. Okay. What you do need for sure to know is x is between -3 and -2. Okay, so x, you don't even need to know the word lies. X is between -3 and -2. Okay, so what that refers to is on a number line, if we have -3, +2, x is somewhere between those. It doesn't include -3 and it doesn't include +2. So x is somewhere in between there. So it could be 0, it could be -2.999, okay, whatever it may be. X is somewhere between those values. Okay. So I'll just talk you through these, and maybe we can actually, let's draw how they appear on a number line. So letter A says x, the set of the set of all values x, such that x is greater than is facing this way, x is greater than 5. Okay, so if x is greater than 5, what that's going to look like is if 5 is here, x is going to be everything greater than that. And we can use an arrow to represent that. So we leave 5 open. It doesn't include 5. So, and by the way, x is an element of the real numbers. So all of the real numbers, every number between greater than 5 is part of that solution. Okay, B, the set of all values x, such that x is less than or equal to 3, and it's an integer. Okay, so x is less than or equal to 3. So because it's equal to 3, we can fill in that hole. Okay, we can fill in 3. It can be 3. X can be 3. And they're all integers. So less than or equal to. So we're only going to highlight the integers. 0, -1, etc. Okay, so we're going to put dots. We're going to put filled in dots on every single integer. And then we're going to do an ellipses just to show that's going to go on infinitely. Okay, we can put an arrow on our number line. Okay, we'll do, we don't need to do all of these, I don't think, but one more, C. So C is the set of all values y, such that y is between 0 and 6. So it doesn't include 0 and 6 because there's no equal sign here. Okay, so y is between, by the way, to show that it's y, we can put a little y in front of our number line, 0 and 6. And because it doesn't say all real numbers, we assume that it is all real numbers. Okay, it doesn't say that it's integers or natural numbers or any other set of numbers. So we don't include 0, we don't include 6 because they don't have an equal sign. Okay, I'm going to do one more, letter F here. So F is the set of all values n such that n is less than 2, okay, less than 2, or n is greater than or equal to 6. Okay, so again, we assume it's all real numbers because it doesn't say otherwise. So we start at 2, so it's less than 2, it doesn't include 2, there's no equal sign here. So we have an open circle at 2, and then n is less than 2, so it goes in this direction with an arrow. And we highlight all of that. Okay, and then n is greater than or equal to 6, so n can be 6, we fill in that circle, and it can be anything greater than 6. So we have an arrow that way. Okay. Okay, interval notation. We can do the same thing as we can with set notation with interval notation. So these two things mean the same thing. So we read this side as x is an element of the values -3 to 2. Okay, x is an element of the set of real numbers between -3 and 2. So notice, with interval notation, we can have our brackets facing outwards, like they did here, or they can be facing inwards. And that depends on whether our equal sign has whether our inequality sign has an equal sign or not. Okay, so whether the value is included or not. So both of these do not have an equal sign, so they're both going to face outwards. Okay. We'll look at a couple of examples. So this next one here, the first one does have an equal sign. So x is between those two values. So we're going to include -3, but we're not going to include 2 because that one doesn't have an equal sign. Okay. Here, in the next example, we're going to include -3, and we're going to include 2 because they both have equal signs. And the third one, this one doesn't have an equal sign. So that one's not included, and 2 is included because it does have an equal sign here. Okay, we're going to do that for the rest of these. If x is just simply greater than 4, so if you think about that on a number line, we're at 4, it's an open circle going forever towards infinity. Okay, so infinity represents the most positive, huge number possible. And so that, so our interval is going from 4, x is going from 4, not including 4, because there's no equal sign, right? So it's going from 4 all the way to infinity. And infinity doesn't stop at a certain point. It's not like all of a sudden we've reached 1,000,000 and then we're at infinity. No, we can always go a number bigger, right? So we don't ever include infinity or negative infinity. Okay. Same here. We've got x is less than or equal to 5. So we're at 5. We're including 5, and it's less than or equal to 5. So when we do interval notation, we're always going to start with the the least number. And in this case, our smallest number, our least number, is negative infinity. So x is going towards negative infinity. It can be anything between negative infinity and 5. And 5 is included because of that equal sign. And negative infinity and positive infinity are never included. Okay, 0 and 8. So not including 0, not including 8, but between the two. So not including 0, not including 8, because there's no equal signs. Okay, between 1 and 4 and including both. So including 1, including 4, and so our brackets both face inwards because there's an equal sign with both. Okay, this one here, between 2 and 7. Not including both of them because there's no equal sign. So not including 2, not including 7. Okay, this one's a little bit different. So we want n to be less than or equal to 3. Okay, so we can include 3, right, because of the equal sign. But then we want it to be less than that. So we want all the values between negative infinity and 3. So we can say not including negative infinity, because we never include infinity, and including 3 because of the equal sign. Okay, or n is greater than 6. So we're at 6, but we're not going to include it because there's no equal sign, and we're going towards infinity. So it can be any number greater than 6 all the way up to infinity. So not including 6, not including infinity. Okay, we're going to write both of these in set notation and interval, all of these in set notation and interval notation. Okay, so set notation, x is greater than 3. It's not including 3 because there's a hole here. Okay, it's going from 3 to infinity, so not including 3, and going, it can be all the way up to infinity. Okay, and by the way, we knew that last one was x because of the variable there. So again, we can say x is less than or equal to -1. Okay, that's this part here. Or x is greater than or equal to 2. Okay, so x is bigger than or equal to 2. So in interval notation, we can go from -infinity to -1. We don't include infinity, and we do include -1 because that point is filled in. Okay, and then we're going from 2, which is filled in, so we include it all the way up to infinity, which we never include. Okay, here, if this is 0 here, and if this is 3 here, we've got 1 and 2 in the middle, or 5. So we can see these are integers, right? So we want the integers from 0 to 6, and we want them to be elements of integers. So that's C in our number sets. Or we can say x is between 0 and 6, and it's an element of the integers. Yeah, you could even put x such that. Okay, here we're looking at x is between 2 and 5, so x is greater than 2 and less than or equal to 5, because it's filled in here but not filled in here. Okay, or we can say x is between 2, so not including 2, and 5. Last one. Oh, 2 more. We've got -1, right? 1, 2, 3, 4, 5. So these are all integers again. So not including 5. So we want x to be, we can say between 4 and -1, and we can include them. Or we can say less than 5 and not include 5. You see how that one's not filled in? And we still have to say that it's an element of the integers. Or we can say from -1 to 4, include that. Or we can say 5, but not include it. And again, we need the element. It's an element of the integers. Okay, last one. So we're not going to include 0 here, and x is just going to be less than 0. Okay, it represents -infinity, that arrow, so we can say between -infinity and 0 in interval notation, and we won't include either of them because we have an open circle, and then we never include -infinity. All right. I'm going to have you pause the video and then practice each of these, okay? And then if you can press play again when you're ready, and actually check your answers, okay? So please. Okay, so here are all of those. Yeah, some things to be careful of. Just don't forget to, like for this one D here, make sure you have, you know, just the integers colored in. Make sure you're not including -5, those kind of things. These ellipses mean that it's going on forever towards infinity. Okay, so we're going to do one more example, and then there's an extension that you can continue to listen to if you're interested. So the members of the set S, we're going to list those, and then we're going to find n of this, which is it's asking a different question. So first we're going to list the factors of 5 in this set. Okay, so the factors of 5, so what numbers multiply to 5? So that's 1 and 5. Okay, we're just going to use, no, doesn't really limit us. We're just going to use the positive integers. We're going to use natural numbers for this. Okay. Okay, the multiples of 5. So that's 5, 25, sorry, 5 times 1 is 5, 5 times 2 is 10, 5 times 3 is 15, 5 times 4 is 20, etc. Okay, prime number is less than 5, so not including 5. Prime number is less than 5. Okay, 1 is not a prime number because the definition of prime numbers is you can multiply it by 1 and itself and you get that number. So 1 is not. 2 is the only even prime number. 3 is a prime number because we can't do anything besides 1 times 3 to get us 3 in terms of using integers. And that's it. 4 is not a prime number, and 5 is not less than 5. So composite number is less than 5. Composite numbers are not prime numbers. So, but neither is 1. So 1's a special one. So just 4. 4 is 1 times 4, it can be 2 times 2. Okay. N of S refers to the number of terms in each set. Okay, so the number of terms. So here we have 2. So n of this set, n of S, is 2 for part A. The number of multiples of 5, well, that's infinite. We could multiply 5 forever and ever and ever. Prime number is less than 5. Well, there's only 2 in this set as well. And composite number is less than 5. There's just 1. Okay, so it's the number of terms in your set. Okay, so if you've had enough. Oh, sorry, just one last thing. Here's some symbols that you might run into. So the E symbol means is an element of. If you have E with a strike through it, like crossed out, it means it's not an element of. This symbol means union, and it's often referred to with the word or. I don't think we'll see these, honestly, but just if you've seen them before and you're curious. This one is intersection, and it means and. And then Z plus refers to the set of all positive integers. So integers, remember, is from like all the negatives onwards. So if we have Z plus, it just means only the positive ones. Okay, so not the negative ones. Okay, so just and not 0 either. 0 is not a positive number, and it's not negative. So just the positive. Okay, here's our extension. If you're curious, keep listening. If you've had enough, no problem. I'm just going to show, remember I mentioned before that repeating decimals are actually rational numbers. I'm just going to show you why that is. So if we have this repeating number, 0.36, that's 36 repeating after the decimal place. We're going to look at why that's a rational number, or how it is. So if we equate that repeating decimal to x, okay? So x is equal to 0.363636 repeating forever. Okay? If we then multiply both sides of that equation by 100, so if we had x equals 0.363636, etc. Okay, we're going to multiply both sides of that equation by 100. Okay, and then we get this. So we have 100x, and when we multiply by 100, that's going to move our decimal place over 2 places, right, on the right side of the equation. Okay, so notice what we get here. That is equal to 36, right, here's the 36 part, plus x. Remember, x is this, so it's all of the 0.36 repeating stuff. So we're going to just write that as 36 plus x. Okay, so 100x is equal to 36 plus x. Okay, so if we solve that equation now, so if we have 100x is equal to 36 plus x, we're going to minus x to the other side. So minus x, we get 99x equals 36. Okay, and if we solve for x, which is here, if we solve for x, we're going to get this. X is going to be equal to 36 over 99 if we divide both sides by 99, right? And then we can simplify that fraction. We can cancel 3 out of the numerator and denominator. So divide by 3, we get 12. Divide by 3, we get 33. We can do it again. So x is divided by 3, that's 4. And divide by 3 here, that's 11. So x is equal to 4 over 11. So 0.36 repeating is actually a rational number because we can write any repeating decimal, no matter what it is, as a rational number, as a fraction. Okay, so that's it for today. Thank you.